Hence, we're now moving on to France. So we are having the next speaker with us, Dr. Veronique Gouraud from Electricité de EDF, Electricité de France, Research and Development. And you're getting ready?
I don't know. Do you hear me? Can you hear me?
Yes.
Thank you. Thank you.
Very good. Welcome, Doctor.
Thanks for the introduction. My name is Veronique Gouraud. I work at Electricity of France, EDF, Research and Development at the National Hydraulic and Environment Laboratory. And I would like to give you in my talk an overview of mitigation measures implemented in France to reduce ecological impacts of hydropower and to share with you the feedback of their implementation. So, first of all, a few words about the context in which these mitigation measures are implemented. In France, as in all countries, we are observing the effect of climate change with an increase of temperature and a decrease of water resources and a decrease of biodiversity in general. In parallel, we have an increasing electricity demand due to the decarbonization of our uses, and we have a development of wind and solar power with an increasing need for flexibility in hydroelectric generation because it is intermittent new renewable energy. In addition, sharing water between uses is more and more complicated because of the scarcity of water resources. So, I mean that the challenge is not simple because we have to implement mitigation measures which allow to reduce ecological impacts in a context of scarcity of water resources, in a context of biodiversity decline, and in a context of increasing needs of electricity. So we have some work. So before describing the mitigation measures which are implemented in France, I would like to give you an overview of hydropower plants in France. So, what are the French hydroelectric fleet characteristics? We have in France 2,500 hydropower plants, which are spread over 250,000 kilometers of river. That corresponds to 25 gigawatt installed capacity that represents between 10 and 14% of the total input. France is the third largest European producer of hydroelectricity, and in France, 75% of reservoirs are used for electricity generation. You have here a map with the location of hydropower plants, which are mainly located in the Seine mountain. So it's very important to underline that in France, there is a high diversity of ecological impacts, which is due to the combination of a diversity of environment conditions with a diversity of hydropower characteristics. On the left side, you have the location of hydropower plants, which are located in 3 mountain chains with very different sediment transport regime. And these hydropower plants are distributed into 37 hydro ecoregions, which are very different in terms of relief, climate, and geology. This is combined with a very high diversity of hydropower plant characteristics because we have a very wide range of power, a large range of head. We have a high number of small hydropower plants in the headwaters with interbasin water diversion, and a small number of large hydropower plants which are more widely distributed across the country. In terms of power generation, 30% of the production comes from storage hydropower plants, and we have 90% of facilities which corresponds to runoff river. So now I would like to focus on the 4 main ecological impacts which are submitted to a regulation in France. There is a river fragmentation and inputment with modified flow and habitat conditions. These habitat conditions are directly linked to the minimum in-stream flow, which is left in the bypass station, and directly linked to the release of turbine water, which corresponds to hydro peaking. We have also an impact due to hydropower plant on the fish migration and the sediment transport. So for each of these 4 ecological impacts, I would like to develop 4 points. The first point is the regulations which are implemented in France to reduce this impact. Secondly, I will describe the mitigation measures which are implemented to respond to these regulations. Thirdly, I will give you brief descriptions of tools and research which help to the implementation of this mitigation measure. And we'll finish by a brief feedback from site experiments which allow to assess the effectiveness of these mitigation measures. So let's go with the minimum in-stream flow. In the French law, the minimum flow which is left in a river has to guarantee the life, the circulation, and reproduction of the living species, such as fish and macroinvertebrates. That corresponds to the definition of ecological flow. So the main issue is to leave enough water over space and over time to preserve habitat for biological communities. And under current regulation in France, there is a minimum in-stream flow, minimum value for the minimum in-stream flow, which has to be greater than 1/10 of the mean annual flow, excepted for 3 cases of derogation or where this value has to be greater than the 20th mean annual flow. Is it also possible to modulate the minimum flow over the course of the year? And concerning the implementation of mitigation measure, according with the French law, in 2014, the value of the minimum in-stream flow was increased by a factor of 4 to improve habitat conditions. Regarding tools which are used to help the definition of ecological flow, we have some habitat models and guidelines which help this definition. And in particular, we have a platform named ABI, which allow to combine hydraulic conditions with species preference. We have also some research studies which allow to assess the effectiveness of this mitigation measure, such as the analysis of long-term monitoring of fish population and the development of a dynamic population model. So just to illustrate and to give some examples, we have implemented in France different experiments to assess the effectiveness of the increase of the minimum in-stream flow. So here the 4 experiments we were conducted on different types of rivers, mountain rivers, plain rivers, and where there was an increase of minimum flow combined with a modulation of minimum flow or combined with unclogging releases to improve the habitat condition, or combined with morphological restoration. On all these rivers, fish and macroinvertebrates were monitored, and tools were developed to analyze the fluctuation in fish and macroinvertebrate communities. What we learned from this experience, is we can return that when we increase the minimum flow, when we modulate the minimum flow, generally we increase the habitat at different degrees according to the morphological conditions. So habitat models are a good tool to assess gains in habitat. In addition, mixing hydrological, sedimentary, and morphological measures increase the chance of success in this improvement of habitat condition, for sure. Nevertheless, it's not so easy to assess gain for biological communities because it is difficult to disentangle the effect of the minimum in-stream flow, of the modulation of in-stream flow, from natural effects, such as from natural factors, such as flood effects and other anthropic pressure. So let's go now to the hydro peaking. So hydro peaking allows to increase hydroelectric power production at hydro dams to meet peak daily electricity demand, and they generate rapid fluctuations in the river. So the issue is to reduce this ecological impact of hydro peaking, and in particular to reduce the stranding and the drift of aquatic organisms, to mitigate the loss of habitat due to rapid increase and decrease of flow. In the French regulation, there is no specific flow rates value that must be respected concerning the hydro peaking. It is a case-by-case definition of hydro peaking operating rules in accordance with the most part of the time with river basin management plans. We have various mitigation measures which are implemented case by case, very different according to site. That may be the increase of backflow or base flow, or a decrease of up and down ramping rate, or a decrease of amplitude or frequency of timing. But there are no new balancing reservoirs because it's very difficult to build these facilities without destroying endangered habitat. Regarding tools which are developing to help to define this mitigation measure corresponding to hydro peaking, we have some hydro peaking indicators, risk assessment, hydraulic models, and guidelines and reference metrics, which help this definition. And concerning research development, long-term fish monitoring and the development of microhabitat selection help to reduce to define mitigation measures concerning hydro peaking. Here you have just two examples to illustrate the experiments which are conducted to assess the effectiveness of this mitigation measure for hydro peaking on biological communities. On the left side, you have an experiment which was conducted on the Dordogne River, where an increase of the base flow and a limitation of the maximum flow was implemented to reduce the ecological impact of hydro peaking. And on the graph, you have the change in trout number over the year, and you can see the gains for trout recruitment. So it's a success story on this river, but it's not always the case because it's often difficult to assess the effect of the mitigation measure for hydro peaking. On the right side, we have an experiment we were conducted on 27 rivers where biological monitoring were implemented from 3 to 17 years into 45 reaches, and a co-inertia analysis of this biological monitoring pointed out that there is a consistent but a secondary influence of hydro peaking on biological communities. So what we learn from this experiment is that if we want to point out the effect of mitigation measure concerning hydro peaking, it's necessary to have long-term monitoring, but it's not sure that that could be pointed out because there are other factors that are operating. It's also important to remember that there are different sensitivities of species to hydro peaking, and there are specific impacts according to site characteristics. For example, stranding of individuals is observed for rivers with secondary channel and gravel bars, whereas drift of organisms is observed for channeled river. Let's go now to the fish continuity with the modification, with the blocking or the delaying of fish migration. So the issue is to enable fish migration, and particularly for didymus species such as eels, salmon, and shad, which travel along long distance to complete the biological cycle. In the French law, there is a classification on rivers in two lists. In the list 1, it is forbidden to build new obstacles. And for the list 2, it is obligatory to restore the ecological continuity in terms of fish migration and sediment transport. In France, the construction of fishway began in 1980 and the downstream passage devices in 2000. And concerning the hydroelectric fleet of EDF, 267 fish passage systems for upstream and downstream were built for 543 obstacles. Knowledge was acquired for the design of the fish passage solution, and there are many guidelines which help the user to build fishways or to define fish downstream passage solutions. And concerning research studies, many studies were conducted to follow the behavior of fish in the fish facilities. And to illustrate that, you have here two experiments which were conducted. In France, on the left side, is an experiment which were conducted on the Rhine River to assess the efficiency of fishways using 10 years of monitoring by RFID telemetry and video. And on the right side, you have a test of downstream passage solution on different sides to test the orientation of bar spacing rates or to test target turbine shutdown or harmless turbine or the addition of repellent effects like light or floating fishways. Overall, what do we learn from all these experiments? That there is more knowledge for upstream migration than for downstream migration, which remain a major challenge. The most part of the time, the efficiency is assessed at the scale of the dam, but there is a lack of assessment at the scale of the reach of the watershed basin and the populations. So it's very necessary to develop that because it's important to assess the cumulative impact of multiple hydropower plants to select appropriate mitigation measures. And to finish, the effect of other drivers reduce the success of mitigation measures, and it's particularly true for the diatomous species which are impacted by multiple pressure. Let's go now to the sediment transport, which is impacted by hydropower plant with a lack of coarse sediment downstream dams and with an occasional release of fine sediment. So the issue is to preserve habitat with, in particular, coarse fraction and geomorphological process, and to limit the impact of fine sediments releases. In the French regulation, mitigation requirements for sediment continuity comes from classification of rivers and from river basin management plans, and there are some threshold standards for fine sediment discharges. So it is concerning the implementation of mitigation measure. It is case by case because it's difficult to define the sufficient sediment transport, which is asked by the French law. But there are some guidelines, handbook, and protocol which allows to assess this sufficient sediment transport. And we use also tools in ecotoxicology to define thresholds for fine sediment. So here you have some examples of different experiments with a gravel augmentation on the Marron River, which allows to increase the salmonid recruitment. And on the right side, an experiment on the Rhine River with a very important morphological restoration through blank erosion and sediment injection. And what do we learn from this experiment? That concerning the sediment injection, it is the durability of this type of measure are questioned. So it is necessary to find solutions to stabilize gravel refill. And concerning the success of morphological restoration, we obtain an increase of habitat heterogeneity and a recovery of riparian biosynosis. But it's important to underline that that morphological restoration can create new ecological niches for invasive species. So let's go to the conclusion and perspective. So, what are the key messages concerning the implementation of mitigation measures? It is important to underline that in France, the legal requirements related to minimum flow and fish continuity are more precise than those related to sediment and hydropicking, or there is a case-by-case approach. Actually, it is often difficult to formulate precise legal requirements because there is a lack of knowledge and the complexity, which arising from the diversity of ecological impacts. So it is not always possible to apply identical threshold, but it is possible to use standardized method, and it is necessary for defining appropriate mitigation measures. So we have to continue to conduct research and pilot studies to improve the knowledge and to clarify which are the proven measures which have to be implemented. And concerning good practices, the key message that I would like you remember, it is that it's important to establish a proper diagnosis to identify appropriate mitigation measures adapted to specific environmental conditions. And for that, it's important to integrate all pressures, all natural factors, and to integrate different scale, local scale, but also basin scale, and to integrate the temporal variability and the climate change. It is also important to carry out environmental and biological monitoring proportional to the risk of ecological impacts. And it's also necessary to have more long-term monitoring if we want to assess the effectiveness of mitigation measures. So I invite you, I encourage you to listen the presentation of a colleague of mine, Laurence Tissot, tomorrow, about this long-term monitoring and which analysis can be done on this long-term monitoring in a regulated and unregulated river. And to finish, just a point on the research of future win-win solution. Solutions which are going to be able to respond to the increasing electricity demand, but also to the reduction of ecological impact in a context of water climate change. And for that, it's important to develop some tools which are going to simulate the optimization of energy production while reducing the water and biodiversity footprint. This is very important to develop this kind of tools on the biodiversity footprint to compare the effectiveness of different mitigation measures. And for that, I encourage you to listen a presentation of another colleague of mine tomorrow morning on the biodiversity footprint of hydropower. And to finish, it's also necessary to identify mitigation measures appropriate to the changing environment and socio-economic context. And I encourage you to listen another presentation of Léa Bech on the uncertainty and complexity in ecological and social mitigation of hydropower. Thank you.